Continue our course Operating Systems Online. Now we are going to cover the topic memory management. Memory is one of the most important resources of a computer system. For a program to be able to execute, it should be loaded into the main memory. Remember that a program that is executing is called as process. If there are more than one process in the system, then memory should be shared among them. Notice that operating system itself is a program, so it should have been loaded into the memory. Average home computer today has 10,000 times more memory than the largest computer in the early 60s. Parkinson's law is saying that programs expand to fill the memory available to hold them. Ideal computer memory should be private, infinitely large, infinitely fast, non-volatile. That means that it does not lose its content when the electric power is switched off, and also should be inexpensive. Memory hierarchy in a typical computer system is as follows. There are a few megabytes of very fast, inexpensive, volatile cache memory, a few gigabytes of medium speed, medium priced, volatile main memory, a few terabytes of slow, cheap, non-volatile, magnetic or solid state storage, some removable storage such as DVDs and USB sticks. Operating system abstracts this hierarchy into a useful model and then manages this abstraction. So here, as it is shown, we have registers. This access time is 1 nanosecond and typically less than 1 kilobyte, and cache memory, and then main memory and magnetic disk. And here the access time and the sizes are written. A memory manager keeps track of which parts of memory are in use, allocates memory to processes when they need it, and also deallocate memory when they are done. In a multi-programming system, a number of processes must be kept in memory in order to share the processor. Partitioning, paging, and segmentation approaches are among possible choices used for memory abstraction. Memory has to manage through memory management algorithms, which may require some hardware supports. In order to be able to load programs anywhere in memory, the compiler must generate relocatable object code. And also we must make sure that a program in memory addresses only its own area, but no other program's area. Therefore, some protection mechanism is also needed in the memory management. If there is no memory abstraction, memory presented to the programmer is simply physical memory. It has a set of addresses from 0 to some maximum, and each address corresponding to a cell containing some number of bits, commonly 8. 3 simple ways of organizing memory with an operating system and one user process is given in the figures. Here in part A, we have an operating system loaded in the low area of the memory, and then comes the user program. In the second one, the operating system is loaded in the high addressed part of the memory, and then in the low memory area we have user program. And here we have a BIOS, which is the part of the operating system already inside the ROM memory, read-only memory, which is not volatile. And we have user program here, and the operating system is loaded in the low area of the memory. The drawbacks of no memory abstraction is, with this usage, multiprocessing is not possible. Multiple threads may be possible, on the other hand. And user programs can easily trash the operating system. Now let's continue with an example on running multiple programs without the memory abstraction. In this example, we have two programs. Each of the programs are 16 kilobyte size. Now consider the first one. The first one has a jump operation at logical address 0. When this program starts execution, it will jump directly to the address 24, where there is a move operation. After the execution of this one, it continues with the next instruction. If we consider the second one, this one is also a 16 kilobyte program. Here there is a jump operation. It jumps to the code at 28. There is a compare instruction at that location. Because no two programs can be loaded into the same address, because of that, the first program may be loaded with starting address 0. After that one, consecutively, the next code is loaded. It is starting with this address. There is no problem for the first program because the starting address is 0 and also the physical address where it is loaded is 0. When this is started to execution, there is a jump operation, jump to the 24. It jumps to the address 24, which is a move instruction, as we considered previously, belonging to the program itself. However, consider the second one. If this one starts execution, there is a jump operation. It's saying that jump to location 28. So it jumps to that location, which is belonging to some other program. This is belonging to the first program. However, it was designed by this jump operation to jump to this compare operation belonging to the program itself. So here there is a problem when we are executing more than one program in a memory without abstraction. For the solution of the problem, we need relocation. Relocation means that if a program is loaded to an address, loaded into memory with a different starting address, then it should execute correctly. History repeats itself in the computer world. Direct addressing, no memory abstraction, is not used anymore in mainframes, mini computers, desktop computers, notebooks, and smartphones. However, no memory abstraction is still common in embedded and smart card systems such as radios, washing machine, and also microwave ovens, etc. No memory abstraction is okay in some embedded systems since, for example, users are not free to run their own software on their toaster. Now let's consider the address space, base, and limit registers. Base register is showing that where the first instruction of the program is loaded in the memory, so the start address of the program. For each program, there is a value to be loaded to the base register when that program is executed. The limit limit register is showing what is the size of the program. So this is showing what is the size of the program for this process. Base and limit registers can be used to give each process a separate address space. When a process references memory, CPU hardware automatically adds base value to the address generated by the process. It also checks whether the address is equal to or greater than the limit register. If so, a fault is generated. If we consider the base register given in this example, here notice that we have a jump instruction for the second one. This is saying jump to location 28. When we are using base register, this address, this logical address, is added to the base register. Because of that, jump 28 becomes jump 16412 when the base register is added. And if we go to that address, this is the address calculated, and the corresponding compare operation is stored there. So with the base register calculation, it works correctly. Keeping all processes in memory all the time requires a huge amount of memory and cannot be done if there is insufficient memory. Swapping brings in each process in its entirety, run it for a while, and then put it back on the disk. Memory allocation changes as processes come into memory and leave it. The shaded regions are unused memory. In this example, initially there's operating system and process A arrives to the system and it is loaded just after the operating system. Then comes process B, it is loaded into the memory after process A, and assume that another process C arrives to the system and it is loaded after process B. And then process A terminates, it is removed from the memory, so there is a free area in this region. And then, for example, process D arrives. So notice that because there is a free area here, it is loaded into that free area. And then, for example, process B terminates because it is neighbor to this free area. When the process B removed, the free area, because of process B, should be combined with the neighboring free area. When the free areas are combined, then, for example, if process A is submitted to the system, then it can be loaded into this free area. The programs may grow when they are executed. Because of that, if we are going to load process A and process B into the memory, there should be some room for the growth of the processes. So suppose that initially the process A is smaller and as it is executed, it's requiring some memory and it is growing. So here it is growing in this direction and there is some more free area to grow more. Sometimes we may desire area for data and also for stack area, then it may be allowed some growing area, room for growth after data before stack. So also both the stack and data part may use this room for growth. It is also allowed for the process B. Allocating space for a growing data segment is shown in A, and allocating space for a growing stack and growing data segment is shown in B. Memory management with bitmaps and linked lists are shown through an example. In this example, we have 5 processes in the memory, and they are loaded as shown in this part of the figure. The free area are shown as shaded regions. And for each allocation unit, we have a bitmap. Here, notice that this is saying that there is something. It is full for the unit 0, then for unit 1, etc. For each unit here, if there is 1, it means that it is not free, and here 5 units are reserved for process A. Then comes 3 units which are free, and then continue. Here we have 8 bits in the computer memory word. Then comes another word, and starting with that address, just showing all these locations are full, and we have ones in these locations up to that point. And then we have 2 free units, and continue with the location where the process D is loaded, and it goes in this manner. Here there is a bit for each unit of memory. If it is full, it is shown with 1. If it is free, it is shown as 0. Another approach may be to use linked list to track free area in the memory. Here we have a linked list. This is saying that there is a process here, and starting with address 0, and it's going up to unit 5, and there is a link area showing the next area. This is a free area, and it is starting with address 5. This is the address 5, and it has length 3. Then there is another unit, and then this is saying that there's a process here. It's starting address 8, and it has 6 units. Then comes another process. In fact, it's corresponding to process C, and it is starting with address 14. It has size 4. So it goes in this manner. Here there is another free area. H is standing for whole free area, and this free area is starting with 18, and it has length 2, so it is that one. And we have a process D, and this is for process E, and then there is a whole. It continues like that. And notice that this may be represented either by using bitmaps or by using a linked list. When a process terminates, the neighboring free area should be combined. There may be different cases. For example, before X terminates, it may be like that as given part A. Here we have a process A, then comes process X, and then process B. When this process terminates, and then we have a free area in that location. For the second case, notice that there is a free area neighboring to process X. When it terminates, these 2 free area should be combined as a single free area if linked list is used. Another case is given here. There is a free area here. When X terminates, they should be combined. If left and right side for the process is free, then when it terminates, both left and also right area should be combined with the area reserved for process X.